In this section 7.1 video, we will be focusing on the end behaviors of graphs. Okay, a typical quadratic function. We could have f of x equals a x minus h squared plus k. Now, the a value, it tells me how wide or narrow my quadratic function will be. But it also tells me the direction of opening. Okay. We know that if the A is positive, then my quadratic will look something like that. And if my A is negative, then my quadratic will appear to be something like that. So that A value determines its end behavior. So if we expand that notion to every polynomial function with a degree that is even, just like the quadratic. So if we expand it to include a function where it's x to the fourth or x to the sixth. Now, if the leading coefficient, so that number in front of that x squared, that x fourth to that x to the sixth is positive, then both end behaviors rise toward positive infinity. Or simply, both rise. Okay. Now, that behaves just like a regular quadratic. Now, if the leading coefficient is negative, then both end behaviors fall toward negative infinity. Or we could also say that they both fall. Okay. An example might be y equals negative 3x to the fourth. Whereas up here we could have y equals 5x to the sixth. Okay, plus some other stuff. I don't care about all that other stuff. I only care about what's in the beginning of my function. Now, a typical cubic, my a value also determines a typical cubic. If my a is positive, then a typical cubic looks like this, where we are going to say that it falls to the left and rises to the right. Now, if my a is negative, then my typical cubic behaves like this, where it rises to the right. And falls to the left. Oops, I just said the same thing. For a negative, I'm going to, oops, it rises to the left and falls to the right. So any polynomial where its degree is odd, x to the third, x to the fifth, x to the seventh, any in this family, if the leading coefficient is positive, then it will behave like a normal cubic would, such that it falls to the left and rises to the right. Now, if the leading coefficient is negative, then it rises to the left and falls to the right. So let's try some examples. For each graph, describe the end behavior to determine whether it represents an odd degree or an even degree. State the number of real zeros. So, describe the end behavior. They both fall. This represents an even degree. Polynomial. State the number of real zeros. That would be 2 real zeros because it goes through my x-axis in 2 places. Now, B, it falls to the left. Rises to the right. This represents an odd degree polynomial. And there is 1 real zero. And the last one, they both rise. That means that it is an even degree polynomial. And there are no real zeros because it never crosses the x-axis.